videos. Good morning. This video is for period 2. This is your work for April 8th. Just to make sure that you guys know what's going to be expected of you before I get back. I will be back on campus at the beginning of 3rd block, maybe before the end of 2nd block. So if I come in, I do expect to see you working, and I expect everything to be put back in the location where you found it. If I find graph paper or dial calipers or spring scales or anything out of place, there will be consequences for that. So you need to make sure that you are returning all the supplies to where you found them. So just a quick review of where we are in this activity. This would have been where we left off on Wednesday. You should have measured the length of your spring with no force applied. And so I'm just going to make up a number here so we have an example that you can follow. But let's just say when you had no force applied, your spring was 2.3 inches long. Okay, and you want to make a note of that is the length when there are 0 newtons applied. It's what's called the natural length. So that is a 0, and that is the letter N for newtons. Then what you needed to do was you needed to add a specific displacement onto that length and fill in this column right here on your chart. So everybody last class should have copied this chart with these columns in it. And I know some of you already have it filled in, so you can kind of fast forward through this. But you would do 2.3, and then you would add a 1/4 inch to that to get 2.55. And that's going to go in your chart. And then you're going to add another 1/4 of an inch. So that's going to bring us to 2.8 inches. And then we'll keep adding 1/4 of an inch. So we have 3.05, and I'm about to go off the page over here. Okay, so 3.3 and so forth. Now, what that tells you is how far you need to stretch the spring. So you are going to stretch your spring to 2.55. Now, your group is going to have different numbers in here. You cannot copy numbers from another group. You all have different springs, okay? So you need to make sure that you're using your spring and your numbers, and every single person in your group is responsible for having this chart. So it's not like one person can do it and then just turn it in and put everyone's name on it. Everybody's going to turn in their own chart with their own numbers. So if you're not the person who's actually doing the measuring and recording the numbers, you need to make sure you copy the numbers from somebody in your group who is taking them. Then you're going to take your, see if I can draw a picture here. It's going to be bad. But you're going to take your spring, and you're going to stretch it out, okay? And you're going to stretch it out to whatever length it says. So for like the first one, it would be 2.55 inches. And you're going to measure that on your calipers. So you're going to set the calipers for 2.55 inches and then stretch the spring to 2.55 inches. And then you will have your spring scale hooked onto it. There's your spring scale, okay? And you're going to read the force that it takes to stretch your spring that much. So just for the sake of putting a number in here, we'll say 3.2 newtons. You don't have to put the newtons in the table if you have the newtons in the column heading. Okay. Notice on your spring scale that those tick marks are 0.2 newtons. So each tick mark is going to give you 0.2 of a newton. So if it's in between 2 tick marks, that's going to give you your 0.1 of a newton. You should not have anything more precise than 0.1 of a newton on that because of the way that is scaled. Okay. Then you'll stretch it to, erase this, and you would stretch it to 2.8 inches long, and maybe that takes like 3.6 newtons or 3.7 newtons or whatever. And then you're going to fill in your chart like so. I know some of you on Wednesday, you were able to finish that out. So if you've got those numbers, you can go do a quick double check of them, but whatever you've got is probably fine. I'm going to copy these down. Okay, so once you have your chart, then you're going to get your construct your graph in the graph paper in the back of the room. So let's talk about our scaling our axes. So we know that our independent variable is what goes on our x-axis. So if I can grab my pen, and I'm not going to put my x-axis right on the margin of the paper. Some of you did that for your motion graphs. You kind of went a little bit too close to the edge of the paper. You want your graph to be scaled comfortably to the size of your paper so that you have space to label your x and your y axis. You want to label the quantity that is on the x and the y axis as well as the units being used. You don't want to just label it with the units. So I was a little bit lenient when I was grading them. If you said miles and seconds or meters and seconds for your motion graph, I'd kind of let that go, but you want to like label it like this is displacement, and displacement is being measured in inches. Okay, so when you think about the two variables that we have here, we have length, like the length of the spring or the displacement of the spring, and we have force. So to kind of figure out which variable goes on which axis, you want to think, does the force depend on the length or does the length depend on the force? And usually one of those directions is going to make more sense. So the direction here that makes sense is that the length depends on, I keep opening that up. That is not what I want to do. Depends on, that is DEP for depends on the force. So that means force is our independent variable. So that's what's going to go on our x-axis, and then the length is our dependent variable, so that is what goes on the y-axis. That can be tricky to do, and there are times when you might play around with that, especially if you have two different lengths, so both x and y would be length on that, but for this one we want to make sure that we get this right. So the x-axis is going to be your force, and that is going to be measured in newtons. So on your x-axis I should see the word force, and I should see like N for newtons, that's the unit that we're using. And then on the y-axis, this should be, I'm trying to think of whether I want you to do displacement or I think I'm going to have you do displacement. And that is going to be in inches. Okay, and then if you look at the chart, I can't go back in the PowerPoint to get the chart, but your displacement actually goes from 0 to, we'll say about like, I think the table goes up to 1.5 inches, and have you go up to like 1.75 or 2 inches, and then scale that appropriately. So I'm going to put some tick marks over here. 1.5, like something like that. And then every 2 squares will make that. I can't really fit it in here, but you guys get the idea. 1.25. I think you were able to measure up to 1.5. It depends on your spring. So if your spring starts to stretch too much and you're going to distort the spring, then you want to stop your table. And then your force starts at the 0 newtons, and then that's going to vary, but I'll say that mine goes up to like 5 newtons. Okay, and so we'll do 1, 2, 3, 4, 5. And again, if you label the axis, you don't have to label each individual tick mark with a unit. Kind of makes it a little cluttery. Now for your scaling, you want it to fit the page and then count by something that's convenient. Some of you in your graphs, you were counting like each tick mark was like 3.5 or something. That's a very awkward number to use. So generally we'll count by halves, ones, twos, fives, tens, the numbers that are easy for us to count by. I had a physics teacher kind of call me out on that once on a science fair project. And you want it to comfortably fit the page within reason. So not everything is going to look perfect, but you don't want your graph to do something like this where it's like down here in the corner and you have way too much space on that. I did take off on your motion graphs if you did something like that. And then you're going to plot your points. So you're going to look at your force, and maybe what did I have? I had like 3.2, and so I'll come over here to 3.2, and that would have been my 0.25. So I guess I'm dot there. Let me erase that if it'll let me pull my eraser up. And let's see what else we got. And then I had 3.6, and that was for my half. And it is okay if you need to estimate this. And remember that you do have 0, 0. So when you had 0 newtons on there, the displacement was 0. And then your points might do something like this. Do not force your points into a straight line, okay? Because real life is just messier than that. All right, now to do the line of best fit, we talked a little bit about this in class, and all of you are in Algebra 1 or higher. The more math you've had, the more comfortable you should be with this idea of best fit. But it's the idea of sketching the line in that goes as close to as many of the points as possible. Now, I'm 100% certain that 0 newtons results in 0 displacement. So I do want to make sure that it goes through the origin, okay? And that's important for this being a directly proportional relationship here. And then you kind of, well, let me do one that's not a line of best fit. So if I make my line go like this, that is not the line of best fit because of how far away it is from the rest of these points. But if I do like this, well, that's wavy, but you get the idea. That's also not the line of best fit because it's aiming too high. So we are going to go somewhere in the middle here. So maybe something like this, okay? And you can do one graph for your group. Your group can do one graph. You each have to turn in your own table and your own calculation, but one graph for your group is fine. And what we also want to do is note another point that's on this graph. So notice that like the line that I've drawn doesn't go through any of the points that I plotted. It's possible that you might draw it through a particular point, but it's not necessary. But as I look at this, okay, this looks like what we call a lattice point. Okay, it looks like a really convenient point right there. It's not one of the ones I plotted. But if I look at where that is, that would be 5.5 newtons. And what is that? 1.1. Make sure I did this. 125, 1.125 inches. Okay, so just kind of remember that. So you're going to construct your graph. Make sure you use a ruler. I'll try to remember to leave the markers out if you'd like to make it look pretty. Again, one graph for every group is fine on this. Yeah, one graph on it for every group is fine. Okay. Then you need to write the equation of the line. So you, to do this, to write the equation of a line, and hopefully this is review for everybody, including my Algebra 1 students, you need to have 2 points, okay, because 2 points determine a line. Not necessarily one of your ordered pairs, okay? So if you think back to the graph I just did, my line did not go through any of the ordered pairs. You're just trying to get it to go close, but I picked a point. Now, in this case, you do want to use your y-intercept because you are 100% sure that that is an accurate point. So our y-intercept is 0, 0. 0 newtons results in 0 displacement. And then the other point I picked was 5.5 newtons resulted in a displacement of 1.125 inches. Okay, so that's my other point. You're going to be using a different point, whatever graph your point has. Remember, your formula for slope is the difference in the y's over the difference in the x's. And it's super nice when one of your points is 0, 0. Okay, so I end up with 1.125 over 5.5. You have a calculator handy? Can you do 1.125 divided by 5.5? 0.2045. 0.2045? Awesome. Thank you. Okay, and now we'll use the slope-intercept form of the line. to be able to write the equation. We just found our slope, so that's going to go in for m. And if you recall, you can rewind the video if you need to. The y-intercept in this case is the point 0, 0, so b is equal to 0. So I would have y is equal to 0.2045x. Now, that's totally acceptable to have, but what we often do in science or engineering is instead of using the generic x and y, we'll actually use a variable that will represent what's on those axes. So in this case, the y-axis was the displacement, and the x-axis was the force. And so instead of using x and y, I'm going to use d and f. So the displacement is equal to 0.2045 times the force. Every person in your group needs to have that calculation. So you cannot just steal the equation from your neighbor. So you all have to show me the 2 points. You all have to show me your calculation for slope, and you all have to show me the equation for your line. So that has to be done independently. And then the last thing is you need to make a prediction for the force required to stretch it 1.75 inches. So you want that displacement of the 1.75 inches. So if I wrote this down right, okay, 0. So suppose I need my spring to stretch 1.75 inches. Make sure you plug this in the correct location. That is the displacement. And even if I wasn't telling you that, you know it because of the units. The units are in inches. So force is not measured in inches. You don't want to plug that in for the F. That is going to go in for your D. And I will not bother you for another calculation. I'll do it myself. Where is my calculator? There we go. 1.7, oops, let's clear that out. 1.75 divided by 0.2045, and I end up with 8.56 is equal to the force. And so according to this, it will take about 8.56 newtons to stretch my spring 1.75 inches. Now, once you have the equation, you can also use the equation to predict things in the other order. So you could say the like if you had like a 10 Newton force, how far would your spring stretch? And so in that case, you would go and plug the 10 in for the force, and that would stretch it to 0.045 inches. Make sure that you do have the correct units on that. So what you should be turning in by the end of class. Every person in the group needs to have that chart and table filled out with all of your data. You need to make sure you have your name on it. You need to have the every individual needs to turn in the calculation for the equation of the line, including the calculation for the slope and then where you're plugging that slope in. And every individual needs to have this calculation that's right in front of you with the prediction for the 1.75 inches. How much force would that take? Then each group needs to turn in their graph that is appropriately labeled and scaled with your scatter plot on it, your line of best fit, and clearly showing which points you are using for your calculation for the equation for the line of best fit. All of those can be submitted up front on the table up front. You can use the turn-in bin and then stack the graphs up. Again, I'm going to be in at the beginning of period 3, so it's not like they're going to be sitting there all day or anything. Make sure that your calipers, your spring scales, any extra graph paper, markers, anything that you were using for this activity gets returned to the table in the back. None of that should be left on a desk. And I don't care if you're the one in your group that took it out. If you notice it's still on your group, put it back. Make sure all of that gets put back. So this video should clarify everything that you need to do for class. I will be in later, so if you have questions, you can find me later, or you can post it on Teams, and I'll do my best to get back to you.